So yesterday I introduced imaginary time formalism for a finite temperature field theory, and I showed you how one can do perturbation theory. So if you have you write your Lagrangian as some free field, free particle Lagrangian plus some whatever perturbation, then you can systematically expand in this perturbation. And we use this to compute the mass dependence of the pressure. So we consider this quantity, so pressure depends on temperature and on the mass of the particles. And we found that this can be written if for free fields, so no interactions. Actually, that's that this can be written as -1/2 times the scalar field propagator evaluated at separation 0. So both ends of the propagator are at the same point. So this is, in terms of Feynman diagrams, this corresponds to this type of diagram here. So this was our formula. And now we need to evaluate the propagator here in this coincidence limit. And for the propagator, we found that we have delta of x, where x is, for me, is the 4 vector having the time, which is, in my case, it's -I tau. It's imaginary, and then the spatial components. So this is equal to the sum over Matsubara frequencies, and then the integral over all k e to the -I omega n tau plus I k dot x omega n squared plus k squared plus m squared. This was our propagator, and now if we evaluate this at in the coincidence limit, then the exponent here becomes equal to 0, and so exponential equal to 1, and then we get what we need to compute is this expression here, delta x equal to 0 equals t sum over n, then the integral 1 over omega n squared plus k squared plus m squared. And then I explained you how one can perform these sums here using this contour trick. So one uses the fact that the Bose distribution function has the poles at these points here in the complex omega plane. The poles are here on the imaginary axis at I times integer multiples of I times all the Matsubara frequencies here. Yeah, and then we could write this sum here as a contour integral like this. So it goes like this, up here up and here down. So general formula for Matsubara sums was, so if you have t times some sum over the frequencies of some function of I omega n, this is the integral along this contour here, the c of d omega over 2 pi I, and then here comes the 1/2 plus Bose Einstein of omega times h at omega. Okay, so I told you this 1/2 here is a bit arbitrary here. We could put here any constant, but the reason why this is convenient is that this expression in the bracket, square bracket, is you can also write as 1/2 times cotangent hyperbolic of beta omega over 2. I would never use this expression in my lecture, but it's nice because here you see this is an odd function of omega. Cotangent hyperbolic is an odd function, so this here is an odd function of omega. That makes it convenient. Now we want to apply this to this expression here, and what we get is delta at x equal to 0 equals this integral here, and well, let me first write the integrand here maybe. So if I have now I have this is my h of omega. I have this expression where this is being replaced by I omega. Omega n is replaced by I omega. So we can write this as 1 over omega squared minus this here, and I can factorize this as omega minus ek times omega plus ek. So ek is the one particle energy for momentum k. The I? It's the one. Omega minus ek, omega plus ek. Well, this, okay, I mean, this is equal to minus 1 omega squared minus a squared minus m squared, right? Yeah. And then it's that. Yeah, the minus sign, yeah, I mean, we have to keep in mind that this here changes the sign if I replace the omega n by minus I omega. So now this function here, my h, has poles, but not on the imaginary axis, but on the real axis. So I should also include them in this picture here. And so we have our contour along which we integrate. And then we have these two poles. One is at ek, and the other one is at minus ek. Yeah? And now I told you yesterday we want to do the integral by moving these two branches of the contour to plus and minus infinity. And if we do that here, we hit one of these poles and we get contribution from them. Then we use the residue theorem. And what we get, well, let me draw this. So this is then equal to the integrals around this point, and you have to always be careful with the direction. We are mathematically negative here, so we get minus signs in the residue theorem, and then the rest of the contour we can move here, and because this falls off like 1 over omega squared, this is goes to 0. Okay, what is this? Well, this is this function here evaluated at this pole, and let me plug this in. So we have then delta of x equal to 0 is equal to, yeah, I have here a minus sign, and I also have a minus sign because I go clockwise. So get two minuses, so which is plus. And I have from this pole, I have 1/2 plus, so I integrate over k, so of course 1/2 plus f both of ek. And then from this here I have, so the pole is at omega equal to ek, so this thing also becomes ek, so I get 1 over 2 ek. Now what happens with the other pole? So there it is at omega is minus ek, so this here becomes minus 2 ek. but I also get another minus because we know that this is an odd function, which is the total is plus, so we get just the same contribution. And so we get a factor 2 here, so this is times 2. Okay, that's our sum. Now we still have to integrate over momenta, and then we see that the first term is just a constant integrate over all momentum space. Well, not, and then 1 over E, which goes like 1 over K for large K. So this is badly UV divergent, quadratically UV divergent. That is should not come as a surprise, because we know that this here is related to the pressure, to this formula, and we know that in quantum field theory the energy density and the pressure of the vacuum is infinite. I mean, this is famous cosmological constant problem. So if we try to compute the pressure of the vacuum, we get this type of infinities. Now we don't solve the cosmological problem here, cosmological constant problem, and we just take the vacuum pressure to 0. So we just subtract this term and ignore it from now on. Yeah, we should always think when we compute the pressure, we want the difference between the vacuum pressure and our finite temperature pressure. So that leaves us with the integral over the Bose distribution. So subtract the t equal to 0 piece and what is left I call it of x0 is integral over k and f Bose of ek over aek. Yeah, this is now finite because for large momenta the Bose or for large energies the Bose distribution function goes exponential to 0. So this is a finite integral which we can evaluate. And now I'm to keep things simple, we assume that or we neglect the mass for m equal to 0, then this would then give us this derivative evaluated at m squared equal to 0. Then this integral here has only a single scale in it, which is the temperature, which sits here in the Bose distribution function. It has mass dimension 2, so it must be, yes?
Besides making the function symmetric, modulo that fact, this half was arbitrary.
What is
when
it?
You introduced half?
Yeah.
When you went to Matsubara description, you added an half. That was a bit arbitrary, right?
The only reason is really this, that it's odd. Otherwise, I could have left this out, but then I would from this pole I would have gotten f Bose at minus ek.
Yeah,
and then I would have to relate this to f Bose of ek.
Of course, yeah, that could in principle be done. But now you are subtracting exactly this one. It must be exactly same as normal ordering.
I mean, this result is okay, I don't want to do the calculation, but you see, so f Bose of minus e is minus 1 minus f Bose of plus e. And this minus 1 then in the final result gives the same here, because I have the,
Yeah, that's fine.
This must be independent of this choice.
Yeah, that's fine. But when you subtract the divergence, you are subtracting exactly half times that. That subtraction is also arbitrary so far. Is this same as normal ordering?
Yes.
When you subtract divergence,
it's normal ordering, sure. I mean,
Okay, that matches with this half for some reason. Exactly that half.
Yes.
Okay.
Okay, so for m equal to 0, there's only one scale in this integral. It has mass dimension 2, so it must be some number times t squared, and this number is 1 over 12. Okay, now we can use this to compute the correction, the mass correction to the pressure, because yesterday I only showed you the result for exactly 0 mass, and with this result we can now compute the order m squared correction to that. So that gives us contribution to, well, we just have to integrate this with respect to m squared, which is multiplying by m squared, and then we get a minus 1/2, so it's minus 1 over 24th. So we find that the pressure of our, so this is of course for m equal to 0, so the pressure for m squared, m non-zero, is what we found is the t to the 4th, which we had, it's times pi squared over 90, and then we get minus 1/2 times this times m squared, so which is minus 1 over 24 m squared over t squared. And this would, and then there are of course higher order terms in m. Okay? I use this and integrated this, and this gives me the second term. Now you see that it's negative, and one can understand that it's negative without doing any calculation, just by physical intuition, so to say. I mean, you have we started with a massless case, and now we introduce the mass. What does the mass do? It takes some energy of the system, so that there's less energy available for kinetic energy. So it will reduce the momenta, and the pressure is of course caused by momentum transfer of the particles. And if they have less momentum, they can transfer less energy. So this must come negative. I mean, if you do the computation for fermions, the argument also applies, of course, and then it's also negative. The only difference is that this coefficient here is different one. It's a smaller one. Okay, and with this very simple observation, which we could have guessed this result even without doing all this, we can find out something very interesting about the standard model of particle physics. So one simple application is what one can call electroweak symmetry restoration. You know that in the standard model, the masses of the particles all come from the non-zero value of the Higgs field. So we have a Higgs field H, and the masses of say of the gauge bosons W, Z, and all the fermions all come from this having a non-zero value and interacting with these particles. So then the masses are all of the form that is some coupling, could be the gauge coupling, could be Yukawa couplings, times the value of the Higgs field. Yeah. So this value is 100. So this is here is 100, 100. What is it? 74 GeV. Yeah, and this could be of order 1 or very small, and then you get all the masses of the standard model. Now, if we heat up the standard model, then the pressure will have this form at very high temperature. Remember, we got this, we expand here in m over t. So for this to be valid, all the masses of all the particles should be smaller than the temperature. The biggest mass in the standard model is the top mass. So we know that for temperatures bigger than the top mass, meaning 174, well, something around this, GeV, then we know that the pressure of the standard model is of the form that it's some constant times t to the fourth. I mean, this corresponds to this term, but now we have to include all the particles of the standard model, so fermions and bosons, so this will be a very different factor, of course. But what's important is that it's positive. And then we have another positive coefficient, say, call it C2, which corresponds to this term, and this comes with a minus sign here, times t squared plus times m squared. Now, I write the m squared as the value of the Higgs. So I can here, and include this, all these couplings are now included in the C2 here. Yeah? They don't change the sign. So and here I have the value of the Higgs field. Can you see this or not? Who can see this? Ah, I can't. Well, very good. Okay. Just so. Okay. So C0 and C2 are positive. Okay, so what does it tell us? If I now change the value of the Higgs field, if I make the Higgs field smaller, the pressure gets bigger. So if you have in your early universe, you have a region where the Higgs field has a smaller value than outside, then this region would have a bigger pressure. Yeah? So that would expand until it fills the entire universe. And this would go on forever until, well, the Higgs field is just zero everywhere. So from this simple result here, we find that at very high temperature, the electric symmetry is restored, meaning that the Higgs value is zero.
So what is the first term for a fermion? This P equals T to the 4 times pi square by 90.
This one?
Yeah. Yeah.
What is the question? What's about?
Fermion.
No, fermion, I forgot the factor here. It's 720 over some big number. But it's a different factor. It's a smaller one because fermion have the Fermi, the Pauli exclusion, and so. But it's a same order of magnitude.
So whatever you add, it doesn't matter what the spectrum is. C0 is always going to be positive. It doesn't matter what the spectrum is. C0 is always going to be positive.
Yeah. Yeah.
Okay.
Okay. So the conclusion from this is which.
Before you erase, I have one more small question. While you calculate the expression for P here, sorry, I'm pointing towards the screen above and misguiding you. So here, the expression for P, you are calculating it from the integral FB divided by EK and expanding it in high temperature approximation, right?
Yes.
Then that gives you dP dm square. And then you're integrating.
Yeah, then I integrate.
So
that gives me the derivative at m squared equal to 0, and then this is the.
Yeah. So the second term is the first non-trivial term that you're calculating that way, right?
The
second term is the one that you're calculating that way.
Yeah, this one.
Yeah. So t to the power 4 is coming from where? Because it is 1 over t square expansion.
Yeah, I mean this was neglecting all masses, and then the pressure has mass dimension 4, and you have only the temperature.
Okay, fine.
And it was an exercise to check this. what you should keep in mind is you shouldn't try to compute it with a path integral, because this is very difficult.
Sorry, say it again.
You should not try to compute that term from the path integral, because that is a pain.
Okay.
It's remarkably complicated. Okay, so conclusion is that at high t, at t much greater than m top, the Higgs value will be 0 and the electric symmetry is unbroken. Now, if you, this is very rough, and the more precise calculation tells you that this happens, when t is like 100, above 130 MeV. GeV, sorry. Okay, yeah, so that's
Top quark mass. The temperature should be greater than top quark mass.
well, the point is that, if you, this estimate, if you are at high temperature, then the Higgs field also, the value gets gradually smaller, and then this estimate for the top mass is not quite accurate. So that's, but okay. So we have computed we expand the pressure around mass equal to 0, and we found, well, I told you what is the leading order contribution, and we explicitly computed this mass correction. And now you could think, well, could we just continue like this? Could we now expand further, and then we would naively think that the next term would be of order m to the fourth. And this is actually wrong. So let's go back to this expression. Let's call this star here. Go back to star. If in this Matsubara sum, I also have a term where the frequency omega n is 0. Then I have just this. Now imagine that if I expand this expression in m squared, then with each order I get an additional power of 1 over k squared. And you see that if then very quickly this will be divergent for small k. So you get infrared divergences. Yeah, this is the first time that we see this phenomenon here for bosonic fields, that you can get infrared divergences, and which is actually when later appears in many places. But here it's very easy to see. So if we consider the n equal to 0 contribution, which is just t times integral over k then we see that we cannot expand this this is not an analytic function of m squared, because the coefficient would be divergent at small k. In m squared due to IR divergences. So we see that we must treat this somehow separately from the rest. And okay, let's do the integral. Oh, not so easy, because this expression, so before expanding, this is UV divergent. Because here you have d3k, so 3 momenta upstairs and 2 downstairs, that's linearly UV divergent. So what can we do about that? We can So we know from our general result, which I just erased, unfortunately, I had to this integral over k and then f both over blah blah. This included all the terms in the Matsubara sum. We know that this was the temperature dependent part. The other part was temperature independent. We know that the temperature dependent part is UV finite. Okay? So it is UV divergent. So we know that the T dependent part of delta at x equal to 0 is UV finite. It means that if we combine this here with all the other terms in the Matsubara sum, we will, the UV divergence must cancel. So we shouldn't have to worry about it. But of course, in practice, we have to compute this somehow. And to get rid of this, I differentiate this one more time with respect to the mass, because then I get something UV finite. So we consider dm squared of delta of x equal to 0, but not the complete one, but only the one from n equal to 0, from 0 Matsubara frequency, which is this here. This is delta of x equal to 0 for n equal to 0. Then we differentiate this here once, and we get a minus integral over k. Then we have 2 powers of the thing in the denominator. So we have k to the 4th integrated over k. This is UV finite. Yeah. So we fix that problem, and then this integral at non-zero mass is perfectly well defined. And now the I forgot the t here. The only scale in this integral is the mass. The integral has mass dimension -1, so the result must be proportional to 1 over the mass with some number in front, and I think it's 1 over 16. What is it? 1 over 8 pi. It's minus t over 8 pi times m 1 over m. Okay, now we see why we cannot expand in m squared, because this is not an analytic function in m squared. Yeah. Okay, now, so we can now integrate this to get delta at x equal to 0. So this gives us delta at x equal to 0. 0 Matsubara frequency is, so I have here minus t over, this is m to the -1/2, so I get here 1 over 16 pi times m to the, or m squared to the 1/2. Let me write it this way. Yeah. If I differentiate this here with respect to m squared, I get, it's a 1 over 4 pi, sorry. Integrating is different, it's complicated. Yeah. So if I differentiate this here, I get a plus 1/2, which gives the 1 over 8 pi. This is, yeah. Okay. And then finally, we can compute the corresponding contribution to the pressure. by integrating one more time. So the resulting contribution to P is P, let me call it P3, because it will be proportional to P cubed, to M cubed. So that is, we have a minus sign here, so that if I integrate, and then with a minus 1/2 I get a plus, then I have 1/8
Dietrich?
T over, say, I think it was 12 pi, and then M squared to the 3/2. Let's check this. If I differentiate this once with respect to M squared, I get 3/2, which turns this into, so it's 1/4, 1/8 pi. And that is, yeah, and then with a minus 1/2, this is minus 1/2 times this, right? Okay, so this is our result.
But here also again you remove the finite part ambiguity for the IR divergence by doing this M integration trick.
Well,
When you integrate back, you are neglecting one integration constant, which is basically delta x equal to 0 at m equal to 0.
yeah.
And that has the IR divergence. So you are basically removing some part, but what, other than the trick, what is the reason that you removed exactly that?
Well, I removed the M independent part, yeah, which is the zeroth order in this case. I mean, I do this expansion in M, and so what we then find, maybe we can summarize this. Okay, so I get, in this expression, I now get P equals to T to the 4th times pi squared over 90 minus 1/24 M squared over T squared, and then plus M cubed over T cubed times 1/12 pi. And then the next term would be order M to the 4th. Okay, now I have an exercise for you, and I would like you to compute this Matsubara sum here for the case that we are dealing with fermions. In the exercise I gave you yesterday, I asked you to show that the propagator for fermions is antiperiodic. So if I shift by beta, then I get the minus sign. And that changes of course, if you have something antiperiodic, this changes the Fourier series on the frequencies. And I would like to ask you to compute exactly this expression, but with fermionic frequencies. So, exercise. So basically compute the sum in star. I mean, I only really the sum in here. This is not, of course, not equal to the fermion propagator. There will be other terms, but if you do this type of calculations for fermions, you will end up with the same type of integrals. Yeah. So it's a useful exercise. Instead, for fermionic Matsubara frequencies. All right, so this was all about the mass expand. Yes?
This expression for Bodeker, we expected an m of 4 by t power 4 term, but you got an m cubed over t cubed. Is there any reason then we don't get an m over t term as the first question?
That's a very interesting question, and there is a reason, and in what I will show you next, we get such a term. Okay? So what I want to do now is I delete this. I mean, so far we only talked about free fields, no interactions. Now we include those, so we again consider a scalar field, and we write our Lagrangian as the free field Lagrangian plus some interaction part, and the free field is what the one we had so far. It's so minus L naught is 1/2 times d tau y squared plus gradient I squared plus m squared I squared. I have a minus sign here, so if we are in imaginary time, all terms come to the same sign. And then my interaction, I take the self-interaction of the scalar field, so I write L int is minus lambda over 4 times phi to the 4th. Yeah, now I play the same game as yesterday. I put this in the path integral, and I expand the path integral. So I have, remember I had that formula that for the pressure, which was e to the beta volume times the pressure equal this was the partition function. And for the partition function, we found this perturbative expansion. At 0th order, I get the Z naught, the free field limit. And then the next term comes from expanding the exponential with the action, and the leading correction is the expectation value of the interaction Lagrangian. Yeah, and then higher order terms. Okay, so now this is our interaction here. And yeah, so we get, we want to compute the pressure, so we take the logarithm. So which gives us beta times volume times the pressure is, well, here the logarithm gives we have a product, so I get the sum of the logarithms, and the Z naught just gives me the ideal gas pressure, which I call now P naught. So this is ideal gas. And then the next term is the logarithm of 1 plus expectation value of I S int, like this. Now I do perturbation theory, so I expand in this interaction here, so I can expand the logarithm, and this here is this is just, well, to first, I only expand to first order, then this is simply I times S interaction. And the 0 means that I evaluate these expectation values with a free field Lagrangian. Okay, so we see that the first term is the P naught, and so we get an expansion in P equals P naught plus P1 plus and so on, and this is of order lambda. This has one interaction. Now we can plug this in here, and then we see that P1 is proportional to the expectation value of the interaction Lagrangian. Yeah, we get that P1 is, so then I put these terms on the other side, that gives us a T over the volume. T, beta is the inverse temperature, so if I put it on the other side, it's a T over the volume. And then, yeah, expectation value of I is it. So the this, well, we can write this out. This is T over the volume, and you know, I have an I here, and then I have a minus I from the time integration. So this gives us +1. So here I have an integral over tau from 0 to beta, and then I have an integral over all space. Then the expectation value of, well, I have this factor minus lambda over 4 phi squared, and of that the expectation value phi to the fourth of x. Okay, now this is, again, we use translational invariance, so this we can here put equal to 0, and then this here just gives me a volume factor which cancels this, and this gives me a beta factor which cancels this. So this all goes away, and we end up with minus lambda over 4 times phi squared, phi to the fourth expectation value. Okay, now this you can now compute using Wick's theorem, and so we
You actually mean factorial 4.
What is it?
You actually mean factorial 4, lambda by factorial.
He's chosen that conversion.
Yeah, usually it is lambda by factorial 4 that people write. No, I'm there. Yeah, choice.
Okay, I have here it's lambda. It's just 4.
You'll get extra factors upstairs.
Yeah. Okay, so now, okay, now you will, in the next step, you will say, oh, why didn't you choose 1 over 4 factorial? Because now I use Wick's theorem, I get a factor 3. Yeah, okay, but that's, I can live with that. So I get, now I have to contract all the fields with itself, and there are 3 possibilities. So I get a combinatorial factor of 3, lambda over 4 times 3 times, and then I have 2 propagators closed into themselves, which I write like, yeah, which is something we have seen before. So this is just the delta of x equal to 0, this type of object, yeah, and I get 2 of them because I have 4 fields, so I get the square. So, and in terms of Feynman diagrams, this is just this one. Yeah, I have 2 of these blobs, and vertex contains the coupling and the combinatorial factors. All right, the nice thing is that we have already done all the integrals that we need. Yeah, it's the same type of object that we already computed, so we can just use our results. And let me rewrite our result like this. So we had that delta x equal to 0. It has 2 parts. One was the temperature independent part, which was UV divergent, which we subtracted by subtracting the vacuum pressure. Then we got a finite piece, which was temperature dependent. Yeah, this we threw away, and the IT is this t squared over 12 that we found. Okay, now we have to compute the square of that. So what do we get? Delta of x equal to 0 squared. We get I squared plus 2I times IT plus IT squared. this thing here is I is UV divergent, so this thing is also UV divergent, but it's temperature independent. So again, we can subtract it by saying I subtract the zero temperature pressure. So I squared is UV T independent, it's UV divergent, T independent, and subtract by, well, maybe normal ordering or by removing vacuum pressure. So the next term is UV divergent here and also temperature dependent. That is what does that term tell us? Well, we already know that this object here gives us the mass derivative of the pressure. And so, and this factor here corresponds to a renormalization of the mass. I mean, I won't show you this explicitly. I mean, it's like in terms of Feynman diagrams, it would be written like this, where you have some mass insertion, infinite mass insertion, and this would be removed by introducing a mass counter term here. So that's, I mean, you have to renormalize the mass anyway, and that we have to do here too. And if you do that, this becomes finite. So this can be removed by mass renormalization. And the renormalization works precisely the same as at zero temperature. I mean, the infinities we get in finite temperature, in quantum field theory, they always come from very short distances. And if I remember what we can view the thermal path integral, we can think of it as a space-time where the time has been compactified with a finite radius. But if we are at very short distances, we don't notice that it's a finite radius. So if you stand here and go outside, you can think that Earth is a flat disk because we are just probing short distances, and same here. And that means that at short distances you don't feel this and you get the same type of UV divergences. Okay, so we all do all this. So we can get rid of these terms, and the only term which survives is the IT squared. And there we have the result. So what do we get? So we find that P1 equals to, we have a minus sign, then we have 3 over 4 times lambda, and then the IT squared. And that's it. So it's t to the 4th over 12 squared, which is, I don't know, 12 squared is, yeah, yeah, but let me write this as 4 times 12 is 4 times 3, so it's 4 squared times 3 squared. Let me write it like this. Then I can cancel the 3, and I get minus t to the lambda t to the 4th over 4 cubed times 3. Sorry, I have forgot something. Well, this is just for the leading order in m over t. Now I can go further and also include the next order, which is here. So this is, and then we see that this is now of order m. This gives a no, wait, I should write this. Now include the mass corrections. Include mass corrections. Then we have IT equals to what I just had, t squared over 12. And the mass correction is this one here, minus t over 4 pi times m squared. No, wait. It's m, yeah, I'm sorry, it's m, yeah. And now I have the answer to your question. So because now if I include this correction here, I get IT squared is t to the 4th over 3 times 4 squared, 12 squared. And then I have a mixed term, which is t cubed times 12 times 4 pi times m. And there you get this term that you mentioned. It's a linear in m. Yeah? You indeed get this at the next order. And then the square of this is plus t squared over 4 squared times pi squared times m squared.
Should be a factor of 2 in the second order.
I forgot a factor of 2 here, yes. Sorry. Yeah. Right. Now, let me just copy this from my, before I forgot more factors of 2, let me just take this from my notes here. So what I find is keeping only this here, so I find that P1 is minus lambda over 4 times so I multiply the 3 in here in this expression, so I get only 1 3. I have 3 times 16, which is 48, so I have t to the 4th over 48 minus okay, so many factors. What is it? I get m over 8 pi minus 1 over 8 pi times m times t cubed times m. M plus higher orders. Yeah, so that's what, that's the interesting part, is that now we get, instead of somehow this funny powers of the mass squared, I mean, this is again a non-analytic expression in the mass squared. Before we got this as at order mass cubed, but at the next order we already get it at order m, and so not cubed. And that could make you worried that at even higher orders there could be even negative powers. And this is in fact what happens if you jump already to the next order. I don't write all the terms, and so at order lambda squared, we get the following type of diagrams. Let me write it like this. So we have a among one of the diagrams is this one here. And now let's consider the contribution where here in this loop we have Matsubara frequency 0, omega n equal to 0. Whereas here I write here the IT approximately, I mean here I get the, this is always the same. You see these blobs are always the same, thankfully, and we know them all. Here I have an IT, and I can use it as t squared over 12. Yeah, and here I consider the omega n equal to 0 contribution. What we get is, if we estimate this contribution here, we get, well, we have two vertices. We have two factors of t squared, so that means I have t to the 4th. From the 0 Matsubara frequency contribution, we get a t times an integral over k, and then we have two propagators, which is 1 over k squared plus m squared squared. That's an integral we've already seen, and it is proportional to 1 over m. So that is, so the whole expression here is of order lambda squared t to the 5th over m. Yeah. So here it happens that if we would now try to consider the massless limit, we would get infinity. So this is IR divergent for n to 0. So this could be a problem if we have light particles, like in, for example, QED or so, that we even have massless particles like photons. And then this would mean that we would get a breakdown of perturbation theory. But even when m is non-zero, and you have this small thing in the denominator, the higher terms in the expandant can become bigger and bigger. But so it's R divergent, but even for small non-zero m perturbation theory can break down. So this problem can be solved. I will show you now. Okay. How do you fix that? I mean, we see that this most singular terms, they have this simple structure. They have one loop here in the middle with 0 frequency, and outside they just have these blobs. And if I use this approximation, this is basically evaluating this blob at 0 mass, and that means that this integral is has only one scale, so it is dominated by what we call hard momenta. Meaning that k is of order t and the frequency is non-zero. No, but sorry, by k of order t. We don't need to talk about frequency here. And this is called that's the first example of a so-called half thermal loop. Thermal loop, or simply HTL. Okay, now the question is, how do we fix this infrared divergences? Well, one can convince oneself that the leading at each order in lambda the leading IR divergency comes from one loop with omega n equal to 0 with hard thermal loops attached to it. So in terms of diagrams, that looks like this. So we have this one loop with a 0 frequency, and then we attach these hard thermal loops here. It's this loop integral that we evaluated at, well, we said that we can evaluate it at 0 mass, and it's dominated, it has only one scale, so and what I call hard is the scale k of order t.
I see.
And
could you say that again?
and maybe one should explain what is soft. Well, there's also, people also talk about soft, and that we will see I explain in a moment what.
Could you say that again, please? What are you calling hard?
You mean here?
Yeah.
Is it not clear? So IT, this was this integral. Remember, we had this integral over k, 1 over f both of ek over k squared plus m squared. And if the mass is non-zero, but if m is small, then it's because of the d3k, it will be dominated by high momenta, and that's why it's called hard thermal loop.
I see.
Yeah.
So at every loop order, the IR divergences come only from daisies, like diagrams like that, flowerish diagrams. Is that what I'm supposed to understand?
Can we discuss this in the coffee break?
Okay.
Yeah, because then I could try to finish this part. Yeah, is that okay? You don't look happy. Yeah, you're the boss. I mean, okay, you are the okay. Sorry. Okay, so yeah, so that is the. These are just the contributions we used many times, and here inside we have an omega n equal to 0. Okay? And now what one can do is one can resum all these diagrams. And they have a nice name because they look like a flower. They are called daisy diagrams. And they can be resummed, meaning that you sum over all of them. Arbitrarily many of these petals here. And the rest, well, if you want to do the combinatorics, it's not so easy, but it's to see what happens, one can look at the propagator, because there, if you compute the corrections to the propagator of the scalar field, you get precisely the same structure. Same type of series. Appears for the propagator. Where we have this plus this plus this. Where we know that this blob here is equal to 3 over 4 times lambda times t squared. confuse it. No, it's not. No, it's correct. Yeah. And this thing here we call the thermal mass squared. So what happens if you have a series of this, then so summing them corresponds to adding a mass correction in the propagator, m squared replaced by m squared plus this thermal mass squared in the propagator. So the resummed propagator oh, I forgot the 4. No, no, it's the 4 is correct.
The canonical normalization of the flight for this diagram as a setting, it should have a semantic factor 2. So if you make the 4 linear formula 4 factorial, this sounds like a now it's like any what?
1, no.
Yeah, which is off because that diagram has a Z2.
Yeah.
So the 8, I mean, canonical normalization 8 has a famous 8 because 8 has a Z2, Z2, Z2. So this has a Z2, it should have a 2. Yeah, probably maybe what I'm asking is why are you using non-canonical normalization?
No, I have, oh, you're right, it's a factor 4. I mean, sorry, this was wrong. Yeah. I have 4 times 3. Yeah, sorry. 4 times 3 over 4, which is then 3 times lambda. Okay, maybe I should, I forgot that 1 over 12
Yeah,
pi. Yeah, no, you're right. I mean, sorry, this was
yeah, so that would
1
be
over
why.
12, yeah. I have 3 times 4 lambda over 4 times t squared over 12, right?
This I'm fine with because now if you make your 4 in the denominator 4 factorial, that gives a half, which is fine.
So what do we have? We have comments 4 times 3. Okay, now it's correct. Okay, yeah. Okay, sorry. So this was what do I get? And there's a plus here, which is not immediately obvious. I mean, you have to so what I get is yeah, t, so it's lambda t squared over 4, and that's the thermal mass squared. Okay, so in the propagator, this corresponds to 1 over for omega n equal to 0. This resummation corresponds to replacing k squared plus m squared by 1 over k squared plus m squared plus the thermal mass squared. And one thing is important. I mean, we should do this only for zero frequency, because if there was also Matsubara frequency here, that would be of order t squared, and the so this transformation is done only for omega n equal to 0, because the m squared, the thermal mass, is of order lambda t squared, and for perturbation theory we must assume that lambda is small, so this term here would always be much smaller than omega n squared. So the non-zero frequency modes, they are not resonant. Yeah, and now the nice thing is that if we have this expression, we have no problems taking the m equal to 0 limit, and we can, for example, if the masses are very small, much smaller than the thermal mass, we can just neglect this here. And then finally we can get, with this knowledge, what the resummation does. It replaces the mass squared by the thermal mass squared. So for m much less than the thermal mass, we can neglect m. And then we can do all the calculations for this zero frequency contribution by just using the thermal mass instead of the zero temperature mass. We have done this calculations. If we have computed everything for, I mean, we have computed all these terms for before we did this resummation, and from omega n equal to 0, we got this expression earlier today, P3 is equal to m cubed over 12 pi times t. And now we use this expression, but with m replaced by the thermal mass squared, and this gives us the sum of all the infinitely many daisy diagrams. So then this tells us that pressure from the daisy diagrams equals to T over 12 pi times the thermal mass cubed, which is T over 12 pi times, where's this, is lambda T squared over 4 cubed, which is, yeah, now, sorry, this is the mass squared, so I have to write 3/2. So I get T to the 4th, many factors downstairs, so the root of 4 is 2, 4 cubed is 8, so I have 8 times 12 downstairs, 8 times 12 pi, and upstairs I have T cubed, T cubed times T is T to the 4th, times lambda to the 3/2. Okay, so this is a remarkable result, because remember in our perturbation theory we started at order lambda, at order lambda to the 0, so no, this ideal gas had no lambda in it. Then we found, earlier today, we found a term proportional to lambda, and then naively you would say, okay, the next term should be lambda squared, but instead we found a smaller power, which was lambda to the 3/2. So that you usually don't see at zero temperature perturbation theory, and yeah, that's this non-analytic behavior you get at final temperature due to these infrared effects. Okay, sorry for being late.
Can I? Hello? I have a question here.
Yeah, please ask. Go ahead. Go ahead.
Sorry.
So, I'm trying to understand. So, you are saying that at higher orders, the temperature dependence only come from these Daisy diagrams. In fact, you can have other diagrams which basically are just function of Matsuura frequencies and not directly any temperature dependence. Is this what you try to argue here? Because if I just take this diagram in the second column from the left, so you can also have contractions between, instead of these hard thermal loops, you can also have contractions between the vertices, right? Which means you may not have temperature dependence. This is what I should understand.
I mean, well, you can think of this as, I mean, okay, you can do, of course, I mean, you can do this here with a non-zero mass, then everything is fine. And then you can sum those, and then at the end of the day you see that you could also take the mass to 0, and then you find this non-analytical contribution. I mean, this is well defined, of course, but if m is non-zero, yeah, if I don't expand in m, then I can compute this in principle, and then I can sum all these diagrams, and then at the end I don't. I mean, it's the thing I wanted to explain next is that maybe a bit more systematic, which uses effective field theories. We can also get the same result by saying we have heavy fields, which is the non-zero Matsubara frequencies and momenta of order t, and then we have light fields, which have 0 Matsubara frequency. And what one can do is one can then say integrate out the heavy fields and get in like top-down integrating out, and then you obtain an effective theory for just the 0 frequency ones. And then you can compute the pressure coming from in this effective field theory. And that's essentially equivalent to doing the sum. The advantage of that method is that you can also use it at to compute higher orders. I mean, with higher orders in this kind of simple-minded approach, it's very tricky, but there you can systematically improve this approximation. Sorry,
I have a question about the product I times IT that you said went into the renormalization, mass renormalization. Yeah, so the IT has a thermal dependence. So this mass renormalization also has a thermal dependence, because you want to resum I times IT and you want to absorb it into the mass renormalization, right?
The IT has temperature dependence, right?
Yeah, so this mass squared, this thermal mass term also has a T squared dependence. So there are two factors now that you have. You have a mass renormalization which is T dependent, and then you have a thermal mass term which is also T dependent.
Let's see. So, I mean, this is the should be the complete IT. So it has a dependence on the mass, and so this mass has to be renormalized, yeah, by mass counter term.
Yes, that's fine. Yeah. So the thermal mass term is not arising from this renormalization process. There is a resummation that gives you the thermal mass, right? The lambda T squared by 4.
So what are you saying? You are saying that this is not of this type, that it's minus T-dependent part times the how do you call the mass counter term, the delta m squared that you get from renormalization?
Yeah, I'm just asking, there are two sources now of mass correction, right?
Yeah.
One is your mass renormalization and one is your thermal mass. So they have very different origins, because now it's like adding twice, right?
Yeah.
You're going to correct your mass with this I times IT, And then you're going to add a thermal mass which is coming from lambda T squared by 4, right? So I'm not able to see the differing origin of the two terms.
I don't know. Maybe one has to write it down more explicitly than
Yeah, okay.
I'm afraid. So then, should we try? And
I will take a look at it. Yeah, okay, sure. Thank you.